So we're going to learn one more derivative rule here, and this one is pretty powerful, but it's also a little more complex, I guess, or it's a little bit more challenging, but it's going to open up a lot more things that we can take the derivative of. Okay, so that's going to be helpful. Okay. So we're going to kind of like figure it out. That's the goal, is to try and like figure out what the derivative or how the chain rule works before we actually come up with the rule itself. And so that's what this is right here. That's what we're calling it an exploration. Okay. So how are we going to do this? Well, so we're going to look at a function right here. F of x equals x plus 3 to the second. And we're going to look at a few functions, okay? And we're going to use the basic power rule to try to find f prime, given this, okay? So right now, the way you guys would find this derivative, okay, is you would need to multiply out x plus 3 times x plus 3, get that polynomial, okay, and then take the derivative to use our power rule. With the way it's currently written, we're technically not supposed to use our power rule here because there's more than just x being raised to a power here. It's x plus 3, right? Just like right here, 2x minus 1. Here it's 3x squared plus 1. Here it's x cubed plus x. It's more than just x being raised to a power. It's like a polynomial being raised to a power here. So the power rule technically doesn't quite apply, but we're still going to use it because it's going to be helpful to see what the actual chain rule is going to be. It's going to help us see that. Okay, so we're going to apply the power rule as if we could, and that'll help us kind of see what the chain rule is going to be. Okay, so use the basic power rule to find the derivative of this thing. All right, so what I mean by that is, again, I'm going to put f prime of x here in like air quotes or just like quotes because it's not going to be f prime of x, okay, but you'll see. Okay. So if we were going to use the power rule here, we have something to the second, right? What should we do with that 2 if we're taking the derivative here? Put it in front, right? Yep, move it in front. So 2 parentheses x plus 3. And then what is our new exponent going to be? 1. Okay, so we have 2 times x plus 3 to the 1. And this can be simplified, right? X plus 3 to the 1 is just x plus 3. So I can distribute that 2 and make it 2x plus 6. Okay. And so say, okay, well maybe if we can just apply the power rule here, maybe the derivative should be 2x plus 6. All right, well let's check it out. So I'm going to draw a little line there. And now we'll do it the way that we know how to do it, right? The way that we know will work. And so we'll take that x plus 3 squared and we'll actually multiply it out. Okay. I guess you could do a product rule now. You don't have to like multiply it out. But let's go ahead and just multiply it out because it's pretty easy to do that. So we'll get what? X squared plus 6x plus 9. Okay. And so now for sure, bless you, bless you again. Okay. For sure the derivative of this, Caitlin, will be what? What's the derivative of x squared going to be? 2x, you got it. The derivative of 6x? Yep, just 6. And the derivative of 9 will be 0, so it's gone. So look at that, right? It actually worked here. The 2x plus 6 and 2x plus 6 match. So like using just the power rule here, okay, gave us the same answer as, well, what it should be. We know for sure 2x plus 6. Multiplying it out, we get the 2x plus 6 there. Okay? So it's like, whoa, hey, that's kind of nice. If this works like we want it to, right, then we won't have to square this and then, you know, multiply it out before we take the derivative. Right? We can just go ahead and just do it from how it's written. Okay? So let's try the next one here. So again, we're going to use the basic power rule to find this derivative here. Okay? And so let's again, I'm going to put g prime of x in quotes to see if it works here. So again, we have something to the second. So again, to take that derivative, we'll bring that 2 in front and multiply by the 2x minus 1. Okay, and then the new power will be just to the 1. Okay. And again, 2x minus 1 to the 1 is just going to be 2x minus 1, so we can distribute the 2, make it 4x minus 2, like that. Okay, 4x minus 2, just like that. So maybe that's our derivative. First one, it worked. First one, it matched up and worked, right? Let's take a look now. So now we'll go and do the actual derivative here. So g of x. So go ahead, find the actual derivative here of g of x. Go ahead, find the actual derivative of g of x. And I'll do that too. Okay, actually I can write it out, I guess. And it's your choice here. If you want, you can use the product rule. First times the derivative of the second plus the second times the derivative of the first. Or you could multiply it out and then take the derivative that way. Okay, do we have an answer yet? Someone want to share? What's the derivative here of g going to be? Natalie, you want to do it? 8x minus 4. There you go. Okay, so it doesn't quite work here, right? For our little shortcut that we're hoping to try and do here, where we just kind of use the power rule here, we have something to the second, right? We would like it just be able to use the power rule, bring that 2 out front, lower the power by 1, and then get our derivative that way. Unfortunately, when we actually multiply things out and get the function expanded there, and then take the derivative, we get 8x minus 4. So they're not the same, but they're pretty close, right? What do they differ by? 2, right? A factor of 2. In fact, if I factor a 2 out here, I'm left with 4x minus 2, which is exactly what we have. So all it's missing from this one is that this one has we're multiplying by an additional 2 there. Okay. Interesting. So pretty close, all right? Go ahead and do the same thing here for number 3 and number 4, okay? Go ahead and try number 3 and number 4, do the same thing. So again, we're going to, find h prime of x for number 3 in quotes by using that power rule, okay? And I'll go through it too. I just won't talk. You guys can, try it on your own there without me, talking there. But go ahead and give it a try. Yo.
If we do Victor and do we find a derivative again? Like we brought the 2 up here and should we have to do it again?
Nope. That's it. That's kind of like the shortcut we're trying to use here. We were trying to see if we can just use that power rule.
4. 4 is 4. You can add 6 actually. You can add 6x. 6x. Yeah. 2.
Yes, try number 4 too. Go ahead and do number 4 as well. Just write it out there. Get it expanded out. And again, you can check my work against yours if you want to. That's fine too. No, we're going to expand to more than just that, but for our sanity's sake, we keep the degree low, because otherwise you'd have to expand out. You know, you have to cube something to actually do it. You know what I'm saying? So it'd be a lot. So just for our sanity.
Yeah. And then that's it. And then you have 2x to the 4. That's the 4. Then you can factor out the cube, but you shouldn't have to factor out.
Okay.
I'm confused.
The chain rule. Okay, so let's take a look at number 3. All right, hopefully you were able to get, for the actual derivative, 36x cubed plus 12x. Okay, and then again, our hopeful derivative, right, where we can, like, we just say, oh, we see something to the second. So let's go ahead and just bring that 2 out front, right, and multiply it, and then lower the power by 1, okay, like this, right? And you can see here, but when we do that kind of like idea, we get 6x squared plus 2. When we get the actual derivative, we get 36x cubed plus 12x. These are not the same, right? But, again, how much do they differ by? This one's a little bit harder to see, maybe, but a 6x. Right? This one right here, if you multiply it by 6x, you get this, right? In fact, I'll just go ahead and factor out a 6x from this. If you factor out a 6x, you get 6x, and then 6x squared plus 2, which is exactly what we've got right there. So again, to get from our shortcut to the actual, we just need to multiply by a 6x. Okay, so there's like a little correction we have to do here, right? A little correction. We're very close, but we have to multiply by 6x. Here again, in letter number 2, we were very close. We just had to multiply by 2. All right, let's go look at number 4 here. Oh, question? Oh, you're good. Okay.
Wouldn't it be 2x? Like you just had for number 4.
Right here.
For number 4.
Number 4.
Yeah. Like you had equals x to the 6.
Uh huh.
On the right side. Why isn't it 2x to the 6?
Because you're multiplying. So the numbers in front are a 1 and a 1, and 1 times 1 would be 1, and then x to the third times x to the third. X to the sixth. Okay. Yep. Okay. And so then we've got now for number 4, again, using that hopeful, kind of shortcut here of just using the power rule rather than having to square this out. We bring that 2 out front, right? Lower the power by 1, so it's a 1, and that simplifies to then 2x cubed plus 2x. Here, okay, if we actually multiply this out, You get x to the 6th plus 2x to the 4th plus x squared. Okay? Take the derivative of that. You get 6x to the 5th plus 8x cubed plus 2x. Now, believe it or not, these also differ, okay, by a factor. So in other words, you can multiply this by something to get this. Okay? And it's a little bit harder to see, so let me see if I can, like, figure it out for us here. So let's go ahead and just factor this thing out. See, I can take out a 2x here, and that leaves behind then 3x to the 4th plus 4x squared plus 1. And then this thing, we can factor it like it's a quadratic. I know it's x to the 4th and x squared here, but it's really, it's a squared term and then a, single term if you think that, if you can kind of see it there. So this does factor. It would be, let's see, a 3x squared, running out of space here, and then an x squared, and I can zoom in, it's not too big to do that. Let's see. Oh, and it has to be plus 1 and plus 1, so that's easy enough. Like that. Okay. And so let's see here. So you can see, well, maybe you can't, but I'll point it out here. So there it is factored, okay? Now if we compare the factored version of the actual derivative to our shortcut here, okay, you can see that what is this one, what is our shortcut missing that this one has? Can you see it? The 3x squared plus 1, okay? This one, so if I were to take that 2x and multiply it with the x squared plus 1, right? So 2x times the x squared would give me 2x cubed. 2x times the 1 would give me a 2x. So and again, all this one's missing is this factor, the 3x squared plus 1. So to go from here down to here, what the actual derivative is, I need to multiply by a 3x squared plus 1. Okay, so there's our correction factor. So, to summarize here, right? In the first example, where we did that little shortcut, there was no difference. There was no correction, it's just we just multiply by 1, right? And it'll be the same thing. And number 2, there was a difference, but we could fix it by multiplying by 2. And number 3, there was a difference, and we fixed it by multiplying by 6x. And number 4, there was a difference, and we fixed it by multiplying by 3x squared plus 1. So, 1, 2, 6x, and 3x squared plus 1, where are those factors coming from? And I'll give you a hint. Look at the original problem there. Their original problems. Where are those factors coming from? Where does the 2 come from? How can we see the 2 from here? How can we see the 6x from here? How can we see the 3x squared plus 1 from here? Where are those coming from? Do you see it? Not the exponents, nope. The derivative of what? Okay, the derivative of, what were you going to say, Grant? Not that. Okay, yeah, it's the derivative of what's inside the parentheses. Exactly right. Okay, what we've got here are functions within functions. Okay, so if you look, right, we have x plus 3 inside a squaring function. Here we have 2x minus 1 inside a square. Here we have, again, 3x squared plus 1 inside a square. And here we have x cubed plus x inside a square. When we went to try and do that shortcut, where we just take the derivative of the something squared and get 2 times that something to the first, okay, what was this derivative missing? It was missing the derivative of what was inside. We never took the derivative of what was inside. And in fact, what was missing from this was the derivative of the thing that was inside the parentheses, right? What's the derivative of x cubed plus x? 3x squared plus 1, right? Same thing here. We took the derivative of the something squared, right? We got 2 times that something to the first. But we have to then multiply by the derivative of what's inside. The derivative of 3x squared plus 1 is 6x. So we need to multiply this by 6x to get the actual derivative. Same thing here, right? 2x minus 1 squared, bring that 2 down out front to the first, but then multiply by the derivative of what's inside after that. Derivative of 2x minus 1 is a 2. And then here, this one didn't need a correction because what's the derivative of x plus 3? It's 1, right? It's 1. And so multiplying this by 1, well, it's still going to end up in the same thing, right? So that's the idea, okay? So we have functions within functions here. Compositions of functions, you might say, right? Or just functions in functions. Okay, so you can turn your paper on the back, and I will give you the chain rule. Okay, so the chain rule okay, and this is the hardest derivative rule that we will be learning, okay, in this class, because it's easy to see a product rule because, hey, we're multiplying two things together, you can use a product rule. Or a quotient rule is easy to see, hey, we're dividing two things, use the quotient rule. The chain rule is a little bit harder to see because we're talking about functions inside of functions. And to be able to see that, that's something you're going to have to develop as you practice and stuff like that. Okay? So, I'm going to do, let's see, how do I want to do this? So let's just do it this way. Let's say y equals f of g of x. And I'm really simplifying this down some. I'm not writing all the, not the gobbledygook I want to say, but the stuff beforehand. This is really what you need to worry about right here for our class. Okay? So if y is equal to f of g of x, so a function inside of another function, then y prime will be f prime of g of x. So the derivative of the outer function, leave what's inside alone, but then multiply by the derivative of what's inside. Okay? So you have functions inside of functions. You take the derivative of the outermost layer, okay? Leave the inner layer alone, and then you multiply by the inner layer. Okay? So with the chain rule, you're looking at functions that have layers, kind of like onions and ogres, right? All right. So, all right, let's try an example. Okay, so again, we're just going to find the derivative, or the derivatives of the following. And we'll just get some practice in here. Okay, number one. F of x equals 3x minus 2x squared to the third. Now, in order to take the derivative of this, must we use the chain rule? Or do we have another option? Could we have taken the derivative of this thing prior to today? If we multiplied it out. So no, if with the way it's currently written, no. Okay? We would have to multiply it out and then we could. So it depends on on what you're trying to answer there. But we could take the derivative of this eventually after we multiplied it out. Of course we have to cube it, so it would be 3x minus 2x squared times 3x minus 2x squared times 3x minus 2x squared. Multiply that all out and then get that to a polynomial to then take the derivative. But now with the chain rule, we don't have to do that. With a chain rule, okay, we can recognize here that we have a function in a function. What's our outermost layer here? Something cubed. Something cubed. What's the derivative of something cubed? 3 times that something to the second, right? You lower the power by 1. Then we multiply by, so times the derivative of what's inside. Okay? So the outer layer, something cubed, was inside the something cubed. It'll be 3 minus 4x, right? It'll be 3 minus 4x, because the derivative of 3x there is going to be 3, and then minus 4x, and then that. Okay. That's going to be times the derivative of what's inside there. Okay. So, you could cube this thing, expand it all out, combine like terms, take the derivative, okay? And it would factor, that derivative would factor to be just this right here. Exactly this. Okay? Or you can just take the derivative using the chain rule. That's so much easier, right? But we're not quite done. No, we are done. Sorry, yeah, that's it. So, that's it. What's that? Nope, you don't need to multiply it out. That's the beauty of this. You can leave it just like that. We've taken the derivative, it's done. How nice is that, right? So much nicer. All right, let's try another one. You're going to multiply it out and actually see if it matches up? Hey, why not? Okay. That's okay. I would do that sometimes when I was in high school as well. I'd be like, I don't believe you, Mr. Widmeyer. So I'll write it out. Do it. All right. Y equals the square root of x squared plus 1. Actually, I would say, I don't believe you, Mr. Grove, or I don't believe you, Mr. Warrenfelds. Yep. Okay, so before we go about taking the derivative here, how should we rewrite number 2? What should we do? First thing before you go take the derivative. Yeah, square roots are no help. So rewrite it as to the 1/2 power. So again, chain rule applies here, right? We have an outer layer, something to the 1/2, inner x squared plus 1. Okay, so something inside of something else. This one we could not do prior to today, okay? Because we don't know, we can't just like square root this thing and expand it out or anything. It doesn't quite work that way with the square root, right? With the 1/2 power there. So here we would have to use the chain rule. Okay? So outermost layer is something to the 1/2. So what's the derivative of something to the 1/2? 1/2, that's something to the negative 1/2 times 2x, the derivative of what's inside. Exactly right. Okay? Again, you could stop here and say, we're done. However, this one does kind of simplify a little nicely. Like the 1/2 will cancel with the what? With the 2 here. Because 1/2 and 2 makes 1. And then this x squared plus 1 to the negative 1/2 we could put in the denominator. X will stay in the numerator, so we'll end up with this. Nope. Nope. But just because I just want to show you that sometimes you can, things do simplify nicely. And now you got to factor it, right? To factor it to match. So you should be able to factor out a 3, right? All those numbers divisible by 3. Okay, so
What's she
pull 3 out to lower your
supposed to
numbers.
end up with?
She should end up with this. She should be able to factor it to this. So in other words, you can see your factors. You should be able to factor out a 3 minus 4x, and then you should be able to factor out a 3x minus 2x squared, and then another 3x minus 2x squared. That's right. All right, let's try another one.
She's determined to finish this.
All right, h of t equals negative 7 over 4t minus 1 squared. Okay, now for this one, if we're going to take the derivative of this, what rule are we going to have to use? Chain and the quotient. Ugh. Ugh. Good question. So if you're going to try and do both here, the primary rule you start with would be quotient. Because what do we have primarily? We have something divided by something. Then within the derivative, so we'll do low, so it'll be this, d high, minus high, d low. When we go to take the derivative of the bottom will require us to then use the chain rule because we have it inside there. Okay? Now, it's not necessary to do a quotient rule here though. How can we rewrite this so we don't have to do a quotient rule?
2 times 14.
When you have something in the denominator, how can we bring it out of that denominator? Make it a negative 2 exponent, right? So we can make it negative 7 times 4t minus 1 to the negative 2, like that. So in here, it's going to be helpful to rewrite it. Okay? Now, eventually, you will have to do chain rules and quotient rules, or quotient rules in chain rules. And of course, there can be product and quotient and chain rules all together in one problem. Okay, so it can get kind of messy. I'm not going to throw that at you today, so I think that's going to be a bit much. I might throw 1 or 2 maybe, but actually the next one will be, so never mind. The next one will be a product rule and a chain rule together. But this one we can avoid it. Okay, so let's go ahead. We haven't taken the derivative, right? We just rewrote it, but now let's take the derivative. So again, since negative 7 is a coefficient, we don't have to use a product rule here. We can just kind of just use their power. So the outermost function here is something to the negative 2. right? Something to the negative 2. So the derivative of that will be, bring the negative 2 out. We get 14. 4t minus 1 to the, what's the new exponent going to be? Negative 3, right? We lower it by 1. Times then, times what? 4. Times the derivative of what's inside, so 4. Okay? And so again, if you want to multiply it out, you would get what? 56 over 4t minus 1 to the third, if you want to like simplify it a little bit. But that's okay too.
Wait, can you go?
Yep, sorry, I'm off the screen.
Where's the 56 from?
4 times 14. 28, and then 28, 28 is 56. Okay? Okay, try one more here.
Is this the first one?
Yeah, do you want me to give you one that's not gross to start out first, maybe?
Is there any like those on the homework?
Are there any like these on the homework? There are some you can practice on the homework, yeah. Mm-hmm.
In my language.
Yeah. Here, let me give you this one. You guys try this one. I'm going to change it up a little bit, though. So we'll say, I don't know, g of a, okay, equals sine of a squared. Okay, so try that one. Okay.
So what is
Yes, ga. Ga equals sin of a. So, what is the outermost function here? What's our outer layer? Sine. So you're going to take the derivative of sine, leave what's inside, times the derivative of what's inside. Mm-hmm. We'll do two yucky ones, and I'll let you guys get some.
Is this the first yucky one?
No. No.
Well, thanks.
This is very unyucky.
I don't like that, no. Every single math class I take it. If it's too easy, it's probably wrong.
What's the derivative of sine?
I mean, if he said what's yucky, then it means that we're going to do
Cosine
two
a
products
squared
in this
times 2a,
combo.
and g prime right there. G prime of a equals. So you don't need the x. It's cosine of a squared. So the x is the a squared. You see what I'm saying? It's like that's what's inside the sine or cosine. Okay, so you should have gotten this. 2a cosine a squared. 2a cosine a squared. All right. Let's take a look at two more here, and then we'll be done. Okay. And they can get yuckier than what I'm going to show you here, but I don't want to go too much. Okay. So, first of all, we could do this one prior to today. Right? In fact, we could do this one prior to yesterday, too. You could just literally multiply this all out and then just use your power rule, okay, to then take the derivative of this thing. Right? But let's not. Right? Let's actually use our rules. So, what kind of rules does it look like we're going to have to use here? Chain and product, okay? Which one first? The biggest picture thing that we've got here, the outermost thing. So you see here, we don't have, like, our function is not something something to a power, right? Our function is not all enclosed by one thing. What's happening is that we have two things being multiplied. So the primary rule we're going to start with is a product rule. Within that product rule, we go to take the derivative of the individual things that are, the things we're multiplying, then we'll have to use the chain rule. Okay? So this is primarily a product rule, and then we go into the chain rule and we take the derivative of the individual pieces. Right? This is not a function to all one thing. Right? Here in number 4, right, there was one function on the outside. It was sine of a squared. Here in number 3, if you rewrite it, it was that, well, the negative 7 is a coefficient, so we can forget about that. But the 4t minus 1 to the negative 2, that was, again, the whole thing was to the negative 2. Here, this whole thing was to the 1/2. Here, this whole thing was to the third. But there's nothing encapsulating this entire function, right? The major piece here is that it's a product of two things that are encapsulated, kind of thing. All right, so that's why it's a product rule first. Then we're going to get into the chain rule when we take that. So to do the product rule, we're going to do the first here. So that's going to be the first. And I think I'm doing my order different than the order that I showed you guys in the notes yesterday, but it's the same thing. So, first here times the derivative of the second. Okay, so now we go to take the derivative of this thing. Excuse me, when we go to take the derivative of this thing, we'll have to do 3 for the power, bring it down out front. 3n plus 1 to the 2, right? Times then the derivative of what's inside 3. I'll put a little plus sign there. Okay? So I'll pause right there to see if people have any questions about what we just did right there. All right, so is everyone okay with this? Any questions about where anything came from? You want me to walk it through again? Sure. Okay, so we did, for the product rule, I did this first function, so this is like my f, and here's like my g. So here's f right here, times, and then here's g prime. This whole thing is g prime right here. That's the derivative of g. Okay? So 3. So the outermost function here is something to the third. You bring 3 out front.
Yeah.
Leave what's inside to the second.
Yes.
Times the derivative of what's inside. The derivative of 3n plus 1 is another. There's going to be a 3 there. Okay? Plus then, now we'll do the second thing here, the 3n plus 1 to the third, times the derivative of the first thing. So what's the derivative of this first thing going to be? It's going to be 2 5 minus n to the 1, or just, leave it alone, times what? What's the derivative of what's inside here? Negative 1. And there's the derivative. That's it. Is that it?
Probably not.
That is it. We don't need to. You can multiply it out if you want to. Simplify it some if you want to, but
That's not really enough to use
Okay.
so long.
it's not too bad to simplify this a little bit more. Let me just show you. We have a GCF here. What's something that's in common to both of these terms? There's only 2 terms here, right? This is one big product. This is one big product. What's in common to both these terms here? Okay. Well, not just an n. What factors?
3n plus 1.
Of 3n plus 1. In fact, they both have 2 3n plus 1s we can factor out, and they both have a 5 minus n we can factor out as well. So we can actually factor out a 5 minus n and a 3n plus 1 squared. And that will leave behind, so let's see, if I take out a 5 minus n, it'll leave behind a 5 minus n still. And then a 9 from the 3 and the 3. And then the 3n plus 1 squared is gone, right, because I factored it out. So I pulled out one of the 5 minus n's and both of the 3n plus 1 squared, so I'm left with a 9 and a 5 minus n. Plus, and if I pull out a 3n plus 1 squared here, I'm left with another 3n plus 1. And then the 2 and the negative 1, so I guess I should have put a negative 2 in front. Squeeze it in front there. And then the 5 minus n, that's gone. Okay, so do you see that there? We factor out 3n plus 1 squared and a 5 minus n. We're left with 9 5 minus n, and then a negative 2 3n plus 1. And that can simplify further, right? You can distribute the 9, distribute the negative 2, combine like terms there. Okay, if you really wanted to. So 9 and 5 makes 45, and negative 2 and 1 will make 43. Then we add that together. So it'd be plus, and then 9 times negative, so it'd be negative 9n minus 6n, so negative 15n plus 43, 45, and then negative 2, 43. Yeah. So look at that. Even like using that product rule, it allows us to like factor it almost fully here. Like, oh, I guess fully, yeah. I guess fully.
Or you factor it all in.
It gets out. Well, I mean, I didn't really. I mean, yeah, we just factored it out. But again, where could you have stopped? You could have stopped right here if you wanted to just find the derivative. There it is. But recognize that you can simplify further if need be. If it matches to a longer choice answer, things like that. Okay. So that's some pretty intense algebra, right? The calculus stopped right there. We have some algebra to do too. Questions on any of that? I will. I want to do one more. All right, one more. Uno más. And then I'll leave you be to do some practice on your own here. But I just want to show you another one here. All right, g of t, last one here. G of t equals e to the 3t minus 1 over t squared plus 3 power.
Why you gotta do that? Why?
Just like that.
Why?
Indeed. Okay?
Yeah.
Okay. So, what kind of rules do you think we're going to be using here? Quotient. Okay, yep. What else? Not the power, because it's e to the something, like our function's in the power, so it's going to be quotient and chain. Quotient and chain. The power rule is, remember, it's like x to a number, okay, or something to a number. For this, it's e to a power there, so that's like a number to a power kind of thing, or a number to a variable kind of thing. So that's a little bit different. Okay. So yes, chain rule and quotient rule. Which one are we going to use first, the chain rule or the quotient rule? Chain first, right? Because the quotient is inside of something, right? So what's the outermost layer here? E to the something. Now, this is the easy part of the derivative. What's the derivative of e to the something? E to that something. So we get another e to the 3t minus 1 over t squared plus 3.
This is the chain.
That's the we're doing the chain rule part, right? Because we have one outermost layer, one kind of like thing that encapsulates the whole problem, and the whole problem is encapsulated by e to the something. Okay, so we take the derivative of e to the something, it's e to the something again. But then by the chain rule, we have to multiply by what? The derivative of what's inside, what the e encapsulates. So we have to take the derivative of the inside thing here, and to take the derivative of this requires the use of the quotient rule. So it'll be the bottom times the derivative of the top, so 3, minus the top times the derivative of the bottom, so, why am I saying 6? 2t, that's a 2. Okay, all over the bottom squared. Okay. Do we need to simplify? Nope. We're done. Okay. So notice the quotient was in the exponent. Quotient was in the exponent, but when we use the chain rule, you multiply by the derivative of what's inside. And so it's not going to be, e to the 3t minus 1 over t squared times, the derivative of what's inside doesn't go up into the exponent. It multiplies outside, okay? So it comes outside like that and multiplies. And there's your derivative, okay? Now, calculus is more than just these kind of like, derivatives and stuff like that, okay? In fact, this is not primarily, I would say, what calculus is all about, but doing this is going to be part of the more important stuff that you'll be doing with the calculus, okay? But this is, helpful to know too, how to do it, okay? All right, on the Google Classroom, I have posted some practice. If you would like to try some things, I gave, there's just a straight up chain rule one. So they all should be just chain rule. There shouldn't be any like product and quotient stuff mixed in. But then I also threw in some problems that have like product rule, quotient rule, chain rule mixed in. Because part of the difficulty of these is that you have to be able to discern where I use which rule, right? Oh, hey, there's a product. I have to use a product rule. Oh, hey, there's a quotient. I have to use a quotient rule. Oh, hey, there's a product inside of a bigger function. I have to use product and chain kind of thing. So there's some practice on the Google Classroom there for you to take a look at and see. All right. So yes. Go ahead. All right. And I'll come around and help, of course.
Do you have a stapler?
I do.
Because this is really thick, and my stapler is a
Yeah,
mini one,
Mr.
so
Wood, they
it
don't
won't-
have an answer.
won't
Oh,
stapling
all right.
well.
Well, we'll see if it works for the. Oh, if you're
Trying
like
to
you have a
keep-
mini stapler, yeah.
Keeping like all of my important notes in a booklet. So
Gotcha.
that, yeah, it won't
This
go
one doesn't
through.
have an answer key.
Maybe I could